Hello, welcome to my talk on stability of floating structures, Part 1, Stability Concept and some examples. In this talk, the focus is on the introduction of the concept and the relevant important factors on how we can increase or adjust the stability of the floating structures. In addition, some examples of the simple structures are given to illustrate the important aspect on stability. We have many different types of floating structures. In this drawing, different types of floating structures are used in the offshore crude oil production, storage, and offloading. The floating structures, including the vertical moored tension leg and the mini TLPs, and the spar type of the floating structure, the semi-submersible structures, and the floating production, storage, and offloading facilities, FPSO. Such operations have been moved to very deep water regions. Many are more than 2,000 meters water depth. Of course, these operations would be very expensive, but the return can be huge if the oil price is high. For instance, TLP, the tension leg platform, is especially used for reducing or removing the heave motion of the structure, because this is the most difficult motion mode for drilling facilities in operation. Now we can see some TLPs are being used for offshore floating wind turbines, but the basic question is how we can reduce the initial cost of such floating wind turbines. In addition, for such a mooring system, the water depth is an important factor. In this slide, I will show two worst maritime disasters of the 20th century. The first one is the famous Titanic at the early of the century, which sank on 15th April 1912 on her maiden voyage. After hitting an iceberg in the Atlantic, the ship sank with more than 1,500 people died, and about 700 people survived from the disaster. The second disaster is the MS Estonia at the late of the century, which capsized on 28 September 1994. During her voyage from Estonia to Sweden, the bow doors were damaged by the large waves, and a large amount of water went into the car decks, causing the loss of the ship's stability, and the ship capsized, with 852 people died, and only 137 survived. If we compare these two maritime disasters, we can see the survival rate for Titanic is much higher than MS Estonia, 31.5% to 14%. So there will be a question: why did so many people die on a modern ship? Unlike the earlier ship, like Titanic, it did not have enough saving boats for saving lives. But the modern ship, like the MS Estonia, must have enough saving boats for everybody on board. But why there are so many people died in the disaster? The answer for this is the time. In sinking of a ship, it would take hours The Titanic took more than 2 hours to sink, but in capsizing, it takes only minutes. Although the full sinking of MS Estonia took about 1 hour, but people were trapped in the capsized ship before her sinking. How can a structure float on the water? For a free-floating structure, we know its buoyancy would be same as the water weight the structure displaces, based on the Archimedes principle. In a simple form, it would be buoyancy equals to the weight of the floating structure. If a structure can be uprightly floating on water, especially for those structures subject to all different dynamic forces, such as wind and wave, we must need enough stability for the floating structure, statically and dynamically. Therefore, sinking happens when the buoyancy is not enough, like the damaged ships. When a lot of water enters the ship, capsizing happens when the stability is not enough. And this stability problem is the focus of this talk. In some special cases, for instance, for the moored floating structures, buoyancy might be larger than the weight of the structure, such as those in the tension leg platforms. And for the floating structure, the system stability must be enough to keep the structure in the upright position. Two type inclinations we need to consider for the floating structure. Heading, which is the inclination along the longitudinal horizontal axis, normally the x-axis for a boat. In this plot, it is pointing out of the screen, and the relevant stability is called transverse stability, which is the most interest problem in this talk and in the practical applications. The second inclination is called trimming, which is an inclination along the transverse horizontal axis, y, in this plot, pointing into the screen. And the corresponding stability is the longitudinal stability. Generally, we have less interest in this, unless the structure length is comparable to the structure weight. To understand the stability of a floating structure, we need to understand 3 centers first. The first center is the center of gravity, G, and this center would be a fixed point for a given loading of the ship, regardless how the structure floats on the water. For instance, in a right-up floating or with an inclination, the center of gravity, G, is fixed. The second center is the center of buoyancy, B. It is the geometric center of the water displaced by the structure. This center is very related to the structure floating status. We will see this later. And the third center is called Metacentre, M, in this figure. Unlike other 2 real centers, this center is not the physical center, but a very important concept. In the right floating position, these three centers would be on the same vertical line, the central dash dot line, see in this plot. When the structure has an inclination, see in this plot, due to the change of the inclination, the buoyancy center would change to a different position. See here. It can be seen the crossing point of the vertical line through the buoyancy center, the blue line, and the structure central line, the dash dot line, is the Metacentre M. In the inclination, the gravitational force and the buoyancy force would be on two different lines, and these two forces make the force couple. Thus, a pure moment would be produced as seen in this plot. Obviously, this moment would make the floating structure back to the upright floating position. Therefore, such a floating system is stable. For a stable floating system, its Metacentre M must be above the center of gravity G. We can examine a case when the center of gravity G is above the Metacentre M. In the inclination, the floating structure, we can see the buoyancy and the gravitational force would make a force couple, but the force couple would produce a moment as this, which would incline the floating structure more. Such a case, the floating structure is unstable, and it would capsize under any disturbance to the floating structure. For obtaining the Metacentre, we need to calculate the metacentric radius Bm. The first step is to calculate the second moment of the water plane area, Ix and Iy. Here, the plot shows how Ix can be calculated using this integral. Here, x times dy is the area of the small area. So its second moment about the x-axis is the y squared times x times dy. So put all this together, we got the second moment of the water plane area, Ix. Similarly, we can calculate Iy, the second moment of the water plane area, with regard to y-axis. So the calculation is by this integral. The second step is the metacentric radius. Bmx is calculated by the second moment of water plane area, Ix, divided by the displacement lambda, and similarly for the metacentric radius along the y-axis, given by this. Now we come to the most important parameter in the stability, the inertial metacentric height, Gm. Here we need to determine three centers: gravity, buoyancy, and the Metacentre, G, B, and M. For the floating structure of a given loading, the center of gravity, G, would be easily determined. And for a floating status, we can calculate the center of the buoyancy easily as B. And from the second moment of the water plane area and the displacement, we can calculate the metacentric radius Bm. So to determine the Metacentre M, if we have all these three centers, we can calculate the inertial metacentric height in a very easy way. If we take the reference point at the keel of the structure, the inertial metacentric height Gm is calculated as Bm plus Kb minus Kg. Or, if we take the center of gravity as the reference, then we can calculate the inertial metacentric height Gm as Bm minus Bg. In the next few slides, we will see some examples of simple floating structures, and some of these structures are the practical structures, and some with the simple simplifications. The first example is the floating spar, and this can be seen in the offshore platforms or floating wind turbines. The floating spar has a relatively small water plane area. In this case, we consider the radius of the spar is 5 meters, and the draft is 100 meters. So we can calculate the displacement simply given as this. It would be 7,854 cubic meters. And we can calculate the second moment of the water plane area given as this. This is a relatively small second moment of the water plane area. Consider the size of the structure. So we can obtain the metacentric radius. It's very small, 0.06 meter. So for this spar, its buoyancy is at the half of the draft. So we can calculate the inertial metacentric height Gm given by Bm plus Gb. So if we want to make a suitable stability for this floating spar, the center of gravity would be below the center of the buoyancy. See this figure. So to make the lower center of gravity, the ballast would be put at the bottom of the spar here. So as an example, a famous floating wind turbine called High Wind is such a floating spar. This floating wind turbine might not be affected very much by the wave, since this relatively small water plane area means transparency in hydrodynamics. But this floating structure must be deployed in deep waters. Generally, the water depth must be considered more than double of the draft. The second example is a barge. A barge is a simple floating structure seen in the plot, which can be often used as a floating platform for different purposes. Here, we consider an example of a barge of 6 meters long, 12 meters wide, and 2.5 meter depth. So the displacement can be easily calculated as this 1,800 cubic meters, and the buoyancy center is half of the draft, is 1.25 meters below the water plane. So based on the size of the barge, we can calculate the second moment of the water area, Ix as this and Iy as this. So we can calculate the metacentric radius Bmx as 4.8 meter and Bmy as 120 meter. So in this case, if we take the center of gravity at the water plane, the inertial metacentric height for this barge would be Gmx is 3.55 meter, and Gmy is 118.75 meters. So from this example, we can see the longitudinal inertial metacentric height is huge when compared to the transverse inertial metacentric height. This is why we normally consider the problem of transverse stability for the floating structure, unless the floating structure has a comparable width and length. Here we have some simple structures. For different structures, the displacement, the center of buoyancy with regard to the water plane, the second moment of the water plane area, Ix, and the metacentric radius, Bm, are calculated. The structures include the hemisphere, that's this, the circular cylinder with the radius r and the shaft h. So the values are given by this. The cone with the radius of r and the shaft h. So we have all these formulas. The frustum is more complicated than the cone. So given by this. ZB is given by this complicated formula, and the square cylinder given by this expression. The fourth example, we will see a semi-submersible with 4 circular cylinders. We assume the cylinder radius is r and the semi-submersible shaft is h. From this plot of the water plane, we can see the distance between 2 cylinders is 2L0. The total displacement is calculated as this. Here, we only include the 4 cylinders for an approximation. However, in the real calculation, all the components underwater must be included. And for the second moment of the water plane area, Iy, it's calculated as this and this. It should be noted, for such a structure, it would be same the second moment of the water area about x-axis or y-axis. So we can calculate Bmy as this. So here we can see the difference of this semi-submersible structure with regard to the single cylinder. Therefore, for this structure, to increase Gm, the stability, i.e., we can increase Bm for achieving the purpose. So we can increase the ratio of the cylinder, we can decrease the shaft of H, and we can also increase the distance R0 to increase the stability of the semi-submersible. In a similar idea, wind float is a famous floating wind turbine, but uses only 3 cylinders. See the picture here. In this slide, we'll show how to increase the stability of the floating structure. This means we need to increase the inertial metacentric height, Gm. So based on the detailed formulation of the inertial metacentric height, Gm, given by this formula, so we can have different way for increase Gm. We can increase the water plane area, so we could have large second moment of the water plane area. So this can be seen for the large floating structure, ships, and the FPSOs, like this floating ship. We can also lower the center of gravity, as we have seen in the spar platform. For this formula, we can reduce kg. we can increase the distance of the waterplane area, like in the semi-submersibles. So we can also reduce their floating structure displacement lambda. We can see the example of the wave radar buoys, which has a relatively small draft, thus the small displacement.